Hi everyone. So this is part of a video series on how to build a balancing robot, and in the previous videos I showed how to modify these servos for continuous rotation, how to build the chassis, and then how to read from a sensor module with a gyroscope, accelerometer, and magnetometer. And in this video I'm going to show how to use a sensor fusion algorithm known as Madgwick's filter, and we're going to use that to get a fairly accurate measurement of our pitch, of the angle of the robot, to see if it's tipping over or not. And so since the last video, well, in the last video I just had the microcontroller breakout board and the sensor module just sitting on my desk. I've since mounted them into the chassis. I'm using some, well, you can't really see it, but some double-sided tape, foam tape, to secure them. I also kind of routed all the wires and got the motors plugged in so that I have a switch that I can turn the motors on and off, so that when I'm doing firmware development I don't have the motors constantly moving and making noise and draining the battery. But yeah, so basically we just have a microcontroller, we have the sensor module, and then these two wires are just for a UART so that I can read out some telemetry. Now just to kind of get a quick look at how it's all working. Alright, so I've got this little test program that I wrote, and when I rotate the robot it will respond. Now as you can pretty obviously tell, the axes don't match up, so like if I spin the robot this way, the cube spins in the wrong axis. And that's just because I didn't want to go to the trouble of fixing all that, so it's just a quick test to make sure that the algorithm was working correctly. But as you can see, it does work. So if I spin it in one axis, it'll rotate one way, in another it'll rotate the other way, and then the other way. So we've got it all. And even if it's moving pretty fast and there's a lot of noise and things are just kind of all over the place, it really quickly gets an accurate, stable measurement. So let's take a look at the code and see how I did it. It's actually really quite easy. Alright, so we're back at the computer now, and the first thing you want to do is get the source code. I'm using Madgwick's filter, so if you search for that, and then the first link should be the one. It's on x-io.co.uk. Yeah, so they kind of explain a little bit here, and there's some demo videos. There's a couple things you're going to want. You're going to want to download the C code, and if you're curious about how it works, you're going to want to download the internal report. So if you download the C code, inside that zip file, you want to go into the Madgwick AHRS filter, or folder, I mean. And there's two files, and you want to copy that into your firmware project. So I'm using Eclipse for this. You can see that I have the two files right here. And I'll kind of review what I've changed since the last video. So if we look down at main, I've got a few things going on. I added a UART to the project. That way, instead of using semi-hosting, I can send text much quicker back to the PC. And so I just have UART set up for 1 million baud, or 1 megabaud, or however you want to pronounce that. Transmitting on PA9. And then the code that I showed in the previous video, I kind of wrapped up into a function. So if I open this function, this is kind of where we were at last time. You guys have probably seen this code before. And so that does all the work of configuring the gyroscope, accelerometer, and magnetometer. And then I use an external interrupt so that I can accurately read the sensor readings whenever they're available. And then I process them in here. So this part is pretty much all the same as before. One thing I did add was I wanted to calculate the gyro offsets at power up, and the way I did that was the first 64 samples, which is a little under 1 second, because I'm sampling at about 73 hertz, I believe. I ignore that first 64 samples because when you first turn on your robot, it's going to be moving, and you want it to be stationary when you are trying to calculate the offset. So you ignore the first, basically first second of data. And then for the next second, I accumulate all of the readings. And then after that, I find the average value. And I store that into the offset variables. And then after that, we just take the raw readings from the gyroscope, subtract the offset, and then we have a fairly clean reading from the gyroscope. And then the rest of it is pretty similar to what you saw before. I convert them into units that I like. So accelerometer into Gs, temperature readings into Celsius. Gyroscope readings are into radians per second, which you actually need it to be in that unit for the Madgwick filter to work properly. And then the magnetometer readings I have in Gausses. The units you use for the accelerometer and the magnetometer are not critical. The Madgwick filter will normalize them so that they have, the vector has a length of 1. But I formatted them this way so that I can look at them and get kind of an intuitive feeling of how it's going and how it's working. And then so after we get all of our readings and I format them how I want, I call an event handler and I give it all of the readings. And that's back in the main file, and it's right here. So this happens to be the event handler that I registered, and it gets all of the readings. They're all floating point numbers. And then the sensor fusion is really, really easy. There's basically one function you call, and it does it all for you. So if you want to do 9 degrees of freedom, where you have gyroscope, accelerometer, and magnetometer all fused together, you would call this function, and you would give it all of your readings. I'm not actually using my magnetometer because for this balancing robot, I don't need to know my heading. And also because when I built the robot chassis, I built it out of metal. And when you have metal, especially a large chunk of metal, close to a magnetometer, it will distort the readings. And I haven't gone to the trouble of doing the soft iron and hard iron compensation algorithms for a magnetometer. So I'm using the IMU version, which is just for gyroscope and accelerometer readings. So yeah, basically you call that function with your new data. And then for my balancing robot, I need to know the pitch, which is, the angle of it, so that if it's falling over or not. And I use this formula, and basically I subtracted half a pi, so that way when the balancing robot is perfectly vertical, we get a pitch value of 0. And when the balancing robot has fallen back and it's laying on its back, we'll have a pitch value of negative pi over 2, or negative half pi. And then when it's fallen over onto its face, it'll be positive pi over 2. And then just for a quick demo, I decided I'd control the motors based on that angle. Just a really crude test just to make sure that things are kind of working. Obviously it is not going to balance yet, but I start off by assigning the motor speeds to 0. And then if the pitch angle is within plus or minus a half radian, I go ahead and power the motors with that angle multiplied by a number. So basically a motor speed value of 0 is going to be no motion. Positive 1,000 will be full speed in one direction, and negative 1,000 will be full speed in another direction. And just from kind of quick testing, I found that with my particular setup, if I took that pitch angle in radians and multiplied by 4,500, I got a somewhat reasonable throttle response to where it isn't going to balance on its own, but it will reasonably well. It'll perform reasonably well, just for a quick test. And then I pass those two speed values to a function that I wrote that controls the H-bridge. And if you haven't seen my earlier video on modifying servos for continuous rotation, check that out. That's where I explain how you need to drive the PWM for the two modified servos. And I show you on an oscilloscope. So it's really easy to write your own code. It's not difficult. And then finally, I wrote a really simple function that will take the 4 values from the quaternion that the Madgwick filter produces, and then I print them out to the UART by DMA. And so that was how we got the that cube going. This guy. And so I wrote a simple Java program that uses Java 3D, and it will take the, if we look over here, we have W, X, Y, and Z are the quaternion values. So down here, Q0, Q1, Q2, Q3, that is what the Madgwick filter code calls the 4 elements of the quaternion. In a mathematical context, they would perhaps more commonly be called W, X, Y, and Z. And so that's what it looks like up here in the corner. And then I have the pitch angle, which is the calculated angle of the robot. And so right now it's actually at 4.5, and that's because when I was messing around, we kind of spun the robot upside down. But if I spin this back, there we go. So now with it laying on its back, it's at about negative half pi for that pitch angle. And with it standing vertically, we're pretty close to 0. So that was my quick test program. I'll include the source code for that so you guys can see it if you want to look at it. And then I'm not using them right now, but I left the code in. Is if I wanted to, I could graph, or well, not graph, but draw a really crude ASCII graph of the acceleration, angular velocity, magnetic field, the quaternion values, and the pitch angle in a console. But since I made that 3D program really quick, I don't really need that. But I left the code in here in case I ever have a need for it. But yeah, so basically it's very little code. All of main is 74 lines of code, and maybe 20 of that is commented out code for telemetry. So yeah, really easy to use. Basically, it's all in the function call, which is either the IMU function or the non-IMU function. So there's 2 things you need to keep in mind, though. If you open the Madgwick ahrs.c file, there are 2 settings. Sample frequency, you must modify that. It needs to be accurate. That'll be how quickly you sample the gyroscope. So I happen to be doing it at 72.7 hertz, and it needs to be accurate because it is going to integrate those values. So if you have it wrong, you're going to get horrible, unusable results. The next thing you'll need to modify is the beta def, which is the default value for the gain of the filter. I have it at 0.1 right now, which seems to work okay, but I have not tuned that. That's one thing I'll be covering in the next video. But yeah, basically those are the only 2 things you really need to mess with, and it just works, which is great. It's a really easy algorithm to use. Alright, so let's see if this thing actually balances. Obviously it won't balance very well because I don't have a PID control loop, but you should see that it is able to balance at least enough for a proof of concept. So I have this toggle switch here on the bottom. Not sure if that's really visible on camera, and that just lets me power off the motor, so I'm going to turn it back on. And we see that it's not perfect, but it is able to balance at least a little bit. But yeah, so there's a lot of work left to do. In the next video, I'm going to show how to do a PID control loop and how to optimize the sensor fusion gain value to get as best results as possible. But yeah, it works pretty well, and it's performing pretty well. So yeah, I'm pretty happy with that for basically no control loop. And as you can see, like if I unpower the motors, it immediately falls over. It doesn't balance on its own very well. Anyway, okay, so there you go. So yeah, that's pretty much it. There's not a whole lot else to cover. Let me show you that Java 3D program that I wrote. So this was the first time I used Java 3D, and it was just a really quick and dirty test. So yeah, this is probably not the best code to look at if you're trying to learn Java 3D, but it works, so I'll go ahead and share it. and basically it's very small. It's 87 lines of code. We create a window, and then we create a canvas, and then a universe, which is where all of your 3D stuff goes, and so on and so on. And so basically the thing you see is the cube, the color cube, and you give it a size, and then you put it in a transform group so that we can transform it. And then okay, so I set the default window size to 800 by 600. I set it so that if you click on the X, it will actually quit the program instead of just hiding the GUI. And then I show the window. And then the second part is a serial port library that I'm using. I've covered this in previous videos for an Arduino, where I show how to send data from an Arduino to a computer, or from a computer to an Arduino. And so if you haven't used this library before, you might want to check out those videos. But it's called jSerialComm, and it's a very easy library to use. And I just hard-coded it. I figured out that my USB UART adapter was COM10, and so I opened that port. I set the baud rate to 1 million, which is what I set up in my firmware. And then I set up the serial port timeout for the scanner mode, because I'm going to use the Java scanner object to read text from the UART. And so if I can't open the UART, I show a very simple error message, and then I quit. But yeah, so we go down here, and then we get the input stream, and we use a scanner object to wait for a line of text to arrive. I get that line of text. I split it up based on spaces, and then that'll give me the 4 quaternion values. And so that's token 0, token 1, 2, 3, and 4, or 0, 1, 2, and 3. And then I multiply x, y, and z, which is q1, q2, and q3. I multiply them by -1 right here, and that just changes the frame of reference. So visually, if you don't multiply those by -1, when you turn your robot, it's going to look like you're turning the camera instead of turning that cube. So you don't have to do the -1, but it just looks a little more accurate. And this is also where if you really wanted that 3D cube to follow the motion of your robot, you would make sure that you map X, Y, and Z to the correct token. So like as you saw, if I rotated my robot along its vertical axis, like a yaw motion, the 3D cube did not rotate in that axis. And that's because I didn't bother to correct this. But again, just a quick test. So if you want that, you can go ahead and basically guess and check and find out which one is which. We then create a quaternion object, a vector for the translation of the object. Now I'm not trying to move that cube. I just want to look at its rotation, its orientation or attitude. So I have the translation vector to be 0, 0, 0. And then we use set transform, and we create a transform 3D object, and we give it the quaternion, the translation vector, and then a scaling value of 1. I then calculate the pitch angle, which I also did in the firmware for the microcontroller, which is right here. But I had the Java program do it as well, just to double check the math. So that's fairly straightforward. I found that with the orientation of my sensor, I needed the W and the Y portions of the quaternion. So for example, you can check by what I did was I assigned X and Z to be 0. So I did like that for X and Z, and I realized that would correctly show just the pitch angle of my robot. In fact, here I'll show you real quick, so you can kind of get a feel for how that works. Okay, so now I know you can't see my robot, but I'm rotating my robot in 3 dimensions, and it's only rotating the cube in 1, and that happens to be the pitch angle. And so that's how you can verify. You just you try setting 2 of the 3 axes to 0 and figure out which one is the one that you actually need. And that'll vary depending on how you have your sensor module positioned. Let me undo that. So I calculate the pitch angle, and then just to verify things, I print out all the values to the console. I have W, X, Y, Z, and pitch. And then, so in theory, this while loop will never exit. It'll be an infinite loop. But if, for example, you unplug your USB UART adapter, we'll no longer have a next line available, and so the while loop will exit. And then I close the scanner, and then I print out a message saying that we lost communication, and then I quit. So anyway, yeah, I'll put this code up, and I'll also put the microcontroller firmware. But as you can see, it's really easy to use, really easy to work with. I may, in the future, use my magnetometer readings and do a 9-DOF sensor fusion. But for this particular project, I don't think I'll have a need for that, so I'm not going to go to the trouble of it. I hope you guys enjoyed the video. If you have any questions or comments, leave them down below. And if you know anybody that might benefit from the video, please share it with them.